Welcome to the unit on equations and inequalities, solving quadratic and linear inequalities using graphs. The objectives for this session are to solve quadratic and linear inequalities using graphs. Recall the steps for solving a quadratic inequality. First, rearrange so that the right-hand side equals 0. Next, solve to find the critical values. Then sketch, and finally use the sketch to find the required values. Pause the video and have a go at the example on your screen. Press play when you're ready to view the solutions. So let's solve example 1a first. Consider the following graph for which the values of x are f of x equals g of x. Let's have a look at the graph on our screen. This is where f of x equals g of x. So, if we try and solve this, we have x minus 7 times x minus 3, which is f of x, is equal to 16 minus 2x, which is g of x. So therefore, if we expand the brackets, and leave the right-hand side as it is, as shown, and then tidy up. So x squared stays as it is. The x's gather together to make minus 8x. And the constants 21 minus 16 is equal to plus 5. And then factorising this quadratic gives us that x minus 3 times x minus 5 is equal to 0. So the point at which x minus 3 times x minus 5 is equal to 0 is either x equals 3 or x equals 5. And so we've solved example 1a. Now for example 1b. When f of x is greater than g of x, we have that either x is less than 3 or x is greater than 5 in these shaded regions. And so we've solved example 1b. We will now go on to solve example 1c. And f of x is less than g of x when x is between 3 and 5, as shown. We will now have a go at another example. Take a look at example 2 on your screen. Pause the video and have a go. Press play when you're ready to view the solutions. So let's solve example 2a first. Suppose f of x equals 8 minus 2x and g of x equals x squared. Find the coordinates of the points of intersection. So take a look at the graph. We have the linear equation f of x and we have a quadratic g of x. Now f of x equals g of x when 8 minus 2x, which is f of x, equals x squared, which is g of x. And therefore, if we rearrange this equation and then factorise, as shown, we obtain that the critical values are either x equals minus 4 or x equals 2. As shown. Now when x equals minus 4, f of x equals 8 minus 2 times minus 4. We've simply substituted the value of x equals minus 4 in the linear equation f of x to give us f of x, or f of minus 4, is equal to 16. When x equals 2, likewise, we substitute x equals 2 into the equation f of x to give us 8 minus 2 times 2, which equals 4. And therefore, when x is minus 4, f of x is 16, and when x is 2, f of x equals 4. And so the coordinates are minus 4, 16, and 2, 4. Now let's solve example 2b. So we have the same equations, and now using part A, we are required to find the solution to f of x is less than g of x. Now f of x is less than g of x in this region here, and clearly this is where x is between minus 4 and 2, as shown. Let's now take a look at graph conventions. What is the difference between dotted and solid lines in a graph? So let's take a look at an example. Suppose this dotted line represents y equals f of x. The shaded region is y greater than f of x. And the unshaded region, or the region shaded white, is y less than f of x. Suppose instead we had a solid line for y equals f of x. Then the shaded region represents the area y greater than or equal to f of x. And the unshaded region, or the white region, represents y less than or equal to f of x. Take a look at this example. On graph paper, shade the region satisfying the inequalities x less than 4, y less than 3x plus 3, y greater than or equal to minus 3, and x greater than 0. Pause the video and have a go. Press play when you're ready to view the solutions. So let's solve example 3. Here's the dotted line x equals 4. Notice that we need to consider this because we're looking at the region x less than 4. Here we have another dotted line, y equals 3x plus 3. And again, we need to consider this because we need to consider y less than 3x plus 3. And now we have a solid line representing y equals minus 3. And notice we need to consider this because we're considering the region y greater than or equal to minus 3. So how do we know what to shade? If y is less than, then we shade below. If y is greater than, then we shade above. And how do we shade if there are restrictions on x? So if x is less than something, then shade to the left of. And if x is greater than something, then shade to the right of. So in this example, where x is less than 4, we have x less than 4 is shaded to the left of the line x equals 4. And going back to y, we have y less than 3x plus 3, so we shade below the line y equals 3x plus 3. So y greater than or equal to minus 3, and we've shaded above the line. And finally, for the region x greater than 0, we're going to shade to the right of the line x equals 0. But where do all these regions overlap? It's here. And this is where all these inequalities are satisfied. Let's check a random point in this region, 3, 0. Does it hold for the inequality x less than 4? For our random point x equal to 3, 3 is less than 4. Does it satisfy the inequality y less than 3x plus 3? X equals 3 and y equals 0. Y is less than, or 0 is less than, 3 times 3 plus 3. Does it hold for the inequality y greater than or equal to minus 3? Since y equals 0, 0 is indeed greater than or equal to minus 3. And finally, does it satisfy the constraint x greater than 0? X is equal to 3, and 3 is indeed greater than 0. So for this random point, certainly, all these inequalities are satisfied. Let's now have a go at another example. Take a look at the example on your screen. Pause the video and have a go. Press play when you're ready to view the solutions. So let's solve this. First, we draw the dotted line for y equals 13 minus x. This is so that we can identify the region y less than 13 minus x. Next, draw a solid line for y equals x squared minus 3x minus 7. And why have we used a solid line? Because we're considering the region y greater than or equal to x squared minus 3x minus 7. So let's recall what we need to do in order to shade regions. If y is less than, then we shade below. If y is greater than, then we shade above the line. So if we're required to shade the region y less than 13 minus x, then we need to shade below the line y equals 13 minus x as shown. And for the region y greater than or equal to x squared minus 3x minus 7, we need to shade above the solid line representing the equality. And the region which coincides with both is the shaded region represented here. Again, let's check a random point. 0, 0 is the easiest. So when we substitute in the equations y less than 13 minus x, we get 0 less than 13. And we substitute in the equation y greater than or equal to x squared minus 3x minus 7, we obtain 0 greater than minus 7. Both of these are true. And so we've checked for one random point in the region. This doesn't serve as a proof, but it does serve as a reassurance. So this brings us to the end of this session. If you have understood its contents, you should be able to solve quadratic and linear inequalities using graphs. Thank you very much for listening. To understand this topic in greater depth, do attempt the exercises in your textbook.